Dr. J. Durga Devi, working as Assistant Professor in the Department of Electronics and Communication Engineering at College of Engineering Guindy, Anna University. Her area of research includes analog and digital circuit design. Her PhD work was CMOS realization of clock generator circuits for microprocessors. She teach electronic circuits, signals and systems, digital VLSI and data converters. She has 16 years of teaching experience.
Welcome to UGC lecture series on practical. Let us see the realization of second order low pass filter, and it is an active filter which will be implemented using op-amp. So, first let us see this ideal characteristic of op-amp. So, this op-amp has an infinite gain in the sense for a finite V out, the input voltage V I D is 0. The next characteristic is it has infinite input resistance. So, input resistance, if it is infinite, the current drawn in its input terminal will be 0, and then it has a output resistance. So, that finite output resistance is 0 here if the case is ideal. If it has finite output resistance is 0, then it acts as a perfect voltage source, and output voltage V out is 0 for 0 V in, and then the bandwidth of this op amp is infinite. So, that is it amplifies the input signal for all frequencies. So, this is considered for ideal op amp. So, we will consider this op amp as ideal and we will realize the filter. So, let us see the frequency response characteristic of the Butterworth filter, which we will be using for realizing. So, the frequency response characteristic of an ideal filter is the one that is shown here. So, the frequency response is voltage gain as a function of frequency. Voltage gain, as we know, it is ratio of V out by V in. V out is output voltage of filter by V in. The frequency response is the frequency of input is varied. So, this frequency is varied and V out is plotted. So, this forms the frequency response characteristic. For an ideal filter, for frequency less than fH, that is input signal frequency less than fH, that is for f less than fH, V out is given by AF multiplied by V in. So, it is constant here up to fH, and for f greater than fH, what is expected is it has to attenuate everything. So, that is V out must be 0 here. So, therefore, the gain is 0 here. So, this is the ideal filter characteristic, ideal low pass filter characteristic. This is closely approximated by the Butterworth characteristic. So, the Butterworth characteristic has a maximally flat pass band, and then what you can see is there is a roll off here. So, this roll off here is after f greater than fH. At f is equal to fH, what you can see is this attenuation is about minus 6 dB at cutoff frequency, and then f greater than fH. So, this attenuation is about minus 40 dB per decade. So, this is a roll off rate for this Butterworth characteristic. So, this is a characteristic which we will use to realize the filter. So, the transfer function of a general second order low pass filter is this. So, we will use this transfer function and we will derive the case for the Butterworth characteristic. So, the transfer function of a general second order filter is there will be a numerator polynomial and then there will be a denominator polynomial. Denominator polynomial is a quadratic one. Numerator polynomial degree must be lower than the denominator polynomial degree or must be equal to. So, this is required when the system is going to be a causal system. Now, for this case of Butterworth, this h of s numerator polynomial is considered to be 1. So, now for the general characteristic we will assume that the numerator polynomial is considered to be 1, and we have a denominator polynomial which is given by s by omega p is a constant here. So, the whole square plus, so there is a coefficient for s here. So, this is 1 by q p by omega p. So, this again is constant plus 1. Now, the magnitude of this filter, okay, h of this transfer function, this is h of j omega mod squared. So, this is given by 1 by these factors here. So, S here stands for S is equal to, so j omega. So, S is equal to j omega is substituted here, and as we know, this h of S here is again a function of frequency, which is V out of j omega divided by V in of j omega. So, this is h of s, that is the transfer function. So, that is given by a numerator polynomial by denominator polynomial. We have taken numerator polynomial as 1, and h of j omega mod squared stands for magnitude of h of s. So, this magnitude of h of j omega the whole square, s has to be substituted with j omega. So, when it is substituted with j omega the whole square, so what you get is minus omega squared plus 1 by q p j omega by omega p plus 1, and if you take this thing a plus j b, and if you find magnitude here, what we get is 1 divided by 1 minus omega squared by omega p squared the whole square plus omega squared by omega p squared q p squared. So, these omega p squared q p squared are constant. So, this is a function of frequency. What we know is omega is j 2 pi f. So, this is h of j omega mod squared. Now, being a low pass filter, at omega equals 0, this h of j omega must tend to 1. So, that is from the general polynomial, as s tends to 0, what you can see here is this term will go into 0, this will be 0, what is left out is 1. So, h of j omega mod of h of j omega will be 1 here. This is at omega equals 0, very close to omega equals 0, h of j omega is closer to 1. Now, we will consider the case omega much smaller than omega p. Omega much smaller than omega p in the sense it is the frequencies which are considered to be the pass band frequencies. So, h of j omega mod squared, in this case if omega is much smaller than omega p, then this factor here will become smaller than 1, and this can be expanded by this using binomial expansion. So, if this is expanded, so what you get is 1 minus 2 omega squared by omega p squared, if we retain the first order term alone in this binomial expansion, plus we have the other term here. Using this approximation, what you can get here is 1 divided by 1 plus 1 by q p squared minus 2 multiplied by omega squared by omega p squared. So, this is we are using only the first order term in the binomial expansion. So, this is the approximated value of magnitude in the pass band. Now, this is where we have come across this h of j omega mod squared is this. So, this is in the pass band. Now, this factor that we have is a constant here. This constant, if it is negative here, this if it is negative, and if we increase this omega from 0 and it is within pass band, if we increase this from 0, this number being negative, so this becomes, as this is increasing, this becomes more negative. So, therefore, this denominator value will reduce. So, therefore, h of j omega the whole squared will increase from unity. So, this is what we have slightly away from omega being 0 within the pass band. So, this case h of j omega increases from unity. So, the characteristic becomes like this. The frequency response, if we plot now, h of j omega mod squared as a function of frequency. So, this at omega equals 0, what we have is unity, and then slightly away from omega equals 0, this h of j omega has to increase from unity within the pass band. So, this is the first case, the case when this is negative, and now we have the other case, the case when this is positive. When this case, when this is positive, this denominator term here, as omega increases from 0. So, this denominator term will increase, and what we have is this h of j omega the mod squared will decrease from unity, that is the second case. What we have is omega h of j omega mod squared. So, this is from unity, what we have is this decreases. So, this is a case for 1 by q p squared minus 2 is positive. So, these are the two cases. Now, the case if you consider this is 1 by q p squared equal to 2, that case what we have is, so this entire term will become 0 and h of j omega mod squared will always be 1. So, the third case that we have is this q p 1 by q p squared minus 2 being 0. So, for this case what we have is for omega away from 0, this response here is flat, here is approximately flat. So, this is a case of Butterworth characteristic, and for this case when this is made to be 0, what we get is QP will be equal to 1 by root 2. So, in the transfer function if we use QP equals 1 by root 2, the characteristic becomes Butterworth characteristic. So, this now if you substitute omega equals omega p in the transfer function, in the general transfer function with QP equals 1 by root 2, the case is being Butterworth characteristic. So, if you substitute omega equals omega p, so if you substitute omega equals omega p here, so what you get here is this term cancels away, and if you have here, so it is QP squared, 1 by QP squared is what we get. So, h of j omega mod squared is equal to 1 divided by 1 by QP squared, or it is h of j omega mod value is equal to QP, and QP here. So, here it is 1 by root 2 if it is Butterworth characteristic. So, at omega equals omega p, h of mod h of j omega must be equal to 1 by root 2, and this being 1 by root 2, it is termed to be 3 dB frequency. So, omega p here is 3 dB frequency, and what we need is QP must be equal to 1 by root 2. So, this is for Butterworth. Now, let us move to circuit realization of the transfer function that we have seen. So, in the filter circuit realization, we will use this op amp here. So, this op amp will be used, and this section is the passive filter section. So, there are two sections of passive filter. So, from the first section of passive filter, output voltage is being connected to the capacitance here. So, this forms the passive filter, and then what we have is an op amp which is connected in non-inverting configuration. The characteristic obtained from this filter will be this, and the cutoff frequency which will see its derivation, which will be given by 1 by 2 pi R2 R3 or these resistances, C2 C3 or these capacitances, and the gain is given by, it is non-inverting configuration. So, therefore, the gain is given by 1 plus Rf by R1. So, let us see this 3 dB frequency derivation here. So, this is this point is taken as V0 here. So, this is the output voltage. So, this is a passive filter, and we will see the relation of V1 in terms of V in, and then we will relate V0 V output voltage in terms of V1, and then we will find out V out relation in terms of V in. So, now with the passive one, so what we have is input here as a function of frequency, it is written as V in of j omega or V in of s. So, this is the passive filter section. So, R2 R3, then what we have is C2 C3, C2 the other side is connected to V0. So, if we use KCL here to express V1 of s to V in of s, so in this node the currents can be equated as incoming current as I1 of s. So, that must be equal to the leaving current. So, that is written here. For simplicity, it is written as I1 instead of writing it as I1 of s. So, this I1 this is equal to, so this entering current I1, this is equal to I2 plus I3. So, these are the leaving currents, and this I1 can be written as this V in minus VA by R2. For simplicity, we will write V in of s as V in and VA of s as VA. So, this is with I1, and then for I2 it is VA, the other node here is V0. So, VA minus V0 by 1 by SC2, this end which is I3, which is VA minus V1 divided by R3, which is VA minus V1 divided by R3, and now V1 this node. So, this V1 can be written in terms of VA using a potential division, because this side what we have is an op amp here which draws 0 current. So, therefore, this forms a loop for us. Using this we can write this potential division expression, wherein V1 is, this is equal to, this is VA is from this node to ground. So, this is V1 is equal to VA multiplied by 1 by SC3 divided by R3 plus 1 by SC3, that is using potential division expression. And then if you simplify here, so this is this becomes 1 divided by SC3 R3 plus 1. So, this is V1 is written as VA divided by R3 C3S plus 1, and you can use VA equals V1 multiplied by this in the expression for KCL. So, if you use this expression, now the variables here will be V in, V1 and output voltage V0. Now, this V1 in terms of V out, if we express, V out here is gain multiplied by V1. So, this V1 is connected to the non-inverting terminal. So, it is this non-inverting gain. So, V1 here can be related to V0. So, V0 here is AF multiplied by V1. So, this again we have to substitute here V1 in terms of V0. So, this is the expression we will have. So, this was the first general case wherein first initially we substituted for VA in terms of V1 and then we will substitute for V1 in terms of V0. So, if we do that, then we can express V0 in terms of V in by eliminating V1. Now, eliminating VA and V1. So, in the previous section, so what we get is an expression for V0 in terms of V in. So, now rearranging the terms with the S squared and then S, the coefficients with S plus a constant. So, this is what we get. So, the general form of H of S in the previous section, what we have seen is 1 by S by omega p the whole square plus 1 by q p omega p into S plus 1. So, these are constants. So, in the same form what we have is this transfer function which is V naught by V in given by A f. So, this brought to the denominator what you have is this S plus 1. So, what is different from H of the general form is here we have a gain here and from this we can get a relation for omega p. In this case it is omega h. So, this omega h squared is given by, so this is 1 by this. So, that is 1 by R 3 R 2 C 2 C 3 and omega h is given by this, 3 dB cutoff frequency is given by this. And here AF is this non-inverting amplifier gain, where AF is given by 1 plus RF by R1. So, there are this being the denominator polynomial will have 2 real roots. So, since it should have minus 40 dB per decade and the cutoff frequency is given by this. So, this is a form that we have seen in the previous section. So, when we write this as a form here, which is by assuming R 2 equals R 3 equals 1, C 2 equals C 3 equals 1, that is with its normalized value. What we have here is S squared plus 3 minus AF into S plus 1. So, the general form here is in place of 1, now we have a constant gain k divided by the denominator polynomial. So, in place of 1 by q p, what we have here is 3 minus AF. So, 1 by q p here is 3 minus AF. So, q p here is 1 by 3 minus k and here k is AF. So, this is non-inverting amplifier's gain which is given by 1 plus RF by R1. Now, we will make another choice here, we will take this as R1. So, AF here is R1 as 1. So, AF here is 1 plus RF. So, with AF as 1 plus RF and if you substitute here with the Q with 1 by 3 minus, so this K being 1 plus RF, what we have is RF is equal to 2 minus 1 by Q. So, what you have here is it is 1 by Q and this is written as 3 minus, in place of K what we have is 1 plus RF. So, this is 2 minus RF. So, RF here is written as 2 minus 1 by Q. So, with the normalized value, the common values are substituted in the circuit. So, all these are 1, R1 is 1, with that RF is 2 minus 1 by Q. So, now we will see design procedure. So, you can choose FH here depending on the cutoff frequency required, 3 dB frequency required for the filter. And the frequency relation is FH is 1 by 2 pi R 2 R 3 C 2 C 3 and if all these are equal, R 2 equals R 3, C 2 equals C 3, what we have is FH is equal to 1 by 2 pi R C. The value of C is chosen as a practical value and once this is chosen, then you can find out what is R. So, the same value of R must be used for both R 2 and R 3. Now, choose R 1 and RF depending on AF. So, this R 1 and RF depending on AF here will depend on Q here. So, with Q being 1 by root 2, so this being 1 by root 2, what you get is AF will be equal to 1.586. With this 1 plus RF by R1, RF we have is 0.586 into R1. So, this is substituted here. So, with R1 chosen as 1, so that is it is being normalized. So, with value of R that you get from the cutoff frequency. So, the same value used in R1 and RF must be taken as 0.586 times R1. So, this is the numerical value which is calculated for a specific example. So, the example here is you will have to design this for a cutoff frequency of 1 kilohertz. C chosen as 0.01, R is taken to be 15.9 kilo ohm, and with AF as 1.56, R1 is chosen as 15.9 K and RF will be equal to 0.586 times R1. So, this comes to about 9.3 kilo ohm. So, this forms the second order low pass filter. So, we will construct this in laboratory session, and as V in is increased from with frequency of V in is increased. So, V out will be plotted and frequency response of this filter will be studied. Let us see the frequency response characteristic of a second order low pass filter with the Butterworth characteristic. So, the Butterworth filter is designed with a passband gain 1.586 and is designed with a cutoff frequency of 1 kilohertz, and since it is a second order, the roll off rate is minus 40 dB per decade. So, we will verify the passband gain, the cutoff frequency and its roll off rate. So, the equipments required for this are power supply, signal generator, oscilloscope, operational amplifier, IC 741 and passive resistors and capacitors, which constitute the filter section. So, here the supply source plus 12 volts and minus 12 volts is derived. So, with the positive terminal here and the negative terminal here, with these two plus 12 volts and minus 12 volts is derived. So, across plus and ground, the plus 12 volts derived is connected to the 7th pin, and from this negative pin to ground minus 12 volts is derived and it is connected to the 4th pin. So, this is with the supply source. The input AC signal that is connected to the filter section is from a signal generator. So, the source set with the sinusoidal signal and a frequency is set with its amplitude. So, an amplitude of about 2 volts peak to peak is set and a frequency now it is set to 200 hertz. Now, this 200 hertz is within the passband. So, a passband signal is now fed to the filter section. The filter section here is two sections of RCs. To the first RC you can see an RC here and then you can see another RC here. So, to the first RC the input signal is fed. So, to the resistor the input signal is fed and the first capacitance, the other end is connected to the output terminal of op amp. So, there is a feedback here which is required for the Butterworth configuration. The second RC section, the R is connected to the positive terminal of the op amp, which is the third terminal, and then is this capacitance which is connected to the ground. These two RC section will constitute the low pass filter. Now, with the resistors here, this is with R1 and RF. So, this RF and this R1 will constitute the gain section for the operational amplifier. So, the resistor values here are 5.6 K for RF and 10 K for R1. So, these two resistors will set the gain of Butterworth to be 1.586 and the RC sections here, R values are chosen to be 150 ohms and the capacitance is chosen to be 1 microfarad. With these values, the cutoff frequency is set to 1 kilohertz. Now, the output from this filter, that is after the operational amplifier, can be observed from the oscilloscope. So, this is the 6th pin here, this is the output of operational amplifier. So, this 6th pin is connected to oscilloscope. Now, the output amplitude, this is a peak to peak voltage, can be measured here. So, this here it is delta y is about 3.11 and the input amplitude here, which is 2 volts peak to peak, which is set here with 2 volts peak to peak, and the ratio between these two gives a gain of about 1.556. So, the required gain from the Butterworth amplifier, that is the filter configuration, is 1.586 and whatever we have attained is very close to 1.586. So, now let us see the cutoff frequency. Now, as the frequency is varied, the amplitude will be attenuated. When it is away from the pass band, the amplitude will be attenuated, and you can see this amplitude getting reduced as it is moving away from the pass band. And at 1 kilohertz, it is a cutoff frequency. So, there it is 6 dB from the maximum. So, we will measure and we will find out whether it is 6 dB. At the cutoff frequency of 1 kilohertz, the measured voltage is 1.7625. So, this is a peak to peak voltage. So, now the gain here, that is 1.7625 divided by 2 volts, this is the input voltage set. So, the gain here turns out to be 0.88. The required gain at 1 kilohertz is 0.78. So, there is a very slight deviation from the required gain. So, this is at the cutoff frequency. So, now let us see the roll off rate. So, we will set this at 1.1 kilohertz, and we will set it at a decade apart, which is 11 kilohertz. We will set the input frequency, we will measure the respective amplitude, and we will see whether there is a roll off of 40 dB per decade. So, first with the setting of 11 kilohertz and the input voltage which is set as 2 volts peak to peak, same as before. Now, the peak to peak amplitude is found to be 26 millivolts, and the respective gain that we get is minus 31 dB. Now, let us see the measure at 1 kilohertz. Now, let us vary the frequency from 11 kilohertz to 1.1 kilohertz. Now, with the frequency set to 1.1 kilohertz, let us measure the amplitude. So, we will use the cursors to measure amplitude. The peak to peak amplitude that we get now is 1.5 volts, and the input frequency is now set to 1.1 kilohertz, which is 1 decade away from 11 kilohertz, and the input amplitude is 2 volts peak to peak. So, with output voltage at 1.1 kilohertz, the amplitude peak to peak voltage that we get here is 1.5 volts. So, this in when you find gain here, so that is this output voltage divided by input voltage. So, the gain that you get here is minus 2.5 dB. The other extreme, which is at 11 kilohertz, which is a decade apart, the output voltage peak to peak that we have got was 26 millivolts, and the gain there is minus 37 dB. So, therefore, the difference in that is minus 35 dB. So, as you go from 1.1 kilohertz to 11 kilohertz, the gain is now minus 35 dB. So, therefore, the roll off rate is now 35 dB per decade. So, which is closer to 40 dB per decade. This roll off rate is verified, and then we have verified the cutoff frequency, which is 1 kilohertz, and we have verified the passband gain, which is 1.565. So, to test your understanding, try to answer the following question. So, the first one could be if this filter is a third order filter. So, try to plot its frequency response characteristic. So, the second question is, so now if the op amp here, if it is connected in an inverting configuration, the one that we have seen is non-inverting, if it is connected in inverting configuration, find out the values of RF in terms of R1 and write the similar component values. So, these are the two questions you can try on your own. So, now let us see application low pass filter. So, this filter being a second order filter, it can attenuate to a larger extent than the first order one, and it can closely approximate the ideal filter. So, this generally can be used in a baseband receiver where it is required to eliminate noise, out of band noise. and the other can be if the signal has to be digitized by using an ADC. So, the out of band signal has to be eliminated. So, in those cases you can use this filter, eliminate out of band signal and then take it to ADC. Thank you.